Because it's so they got this. Well, they start. I don't all you have to do is so funny, read Facebook comments like that. It's not just. It's a video.
Hello, good morning. There's one last homework that is optional, but the contents are not optional, that is due on Friday. How to work for the final exam, the best strategy might be just first look for midterm exams, from this semester 2026, then comes homework. If you want to limit your efforts to the minimum, go through the midterm exams. I think that's what I would say. That's the smallest database you can have. I'm not saying that is that will take you through, but that's the minimum you can have. The smallest database you can get.
So if you say like midterms and homework.
Yes, that should be very, I think if your grades are reasonable and you're not on the border, then midterm plus homework should be sufficient. Homework should be sufficient, yeah, midterms is kind of a smaller database. Midterms are included in homework most of the times. Does that help? Because homework is a bigger database in sense. Yeah. But what I meant there was that if you're planning to put in only 1 hour of effort into this, then midterm exams probably 1 or 2 hours of effort, that is midterm exam. If you want to put in more effort, then it's homework and so on. Does that make sense? That's probably not the correct thing to say.
What about previous year's data? Like,
Sure, that should be good enough. Yeah, okay. Yeah. Like, don't go by my words, don't take it too seriously, because like I've told you how I make the exams. It's not that I go to the final exam and make the exam. So, but homeworks are designed by me, midterms are designed by me, midterms are the ones that are most recently designed by me. So probably it's in my head. That's how it works, I suppose. But don't take these statements too seriously and don't put your strategy into that too much. Right. Was that good enough? But keep doing whatever you have been doing if your grades are not on the border. And if it is on the border, put in a little more effort. No, they're weak, but that's it. This is the last lecture. I'll finish the spherical mirrors, which is part of the homework. Now we are doing ray optics, and in particular, we are working on situations where light can go through an interface. When you have an interface between two medium, light can either reflect into the same medium it was to begin with, or it can get into the other medium. And when it gets into the other medium, we call it refraction. Otherwise, we call it reflection. So we are talking about refraction. We introduced the law that governs refraction ray. And today we want to talk about what if the interface is not planar, it is spherical. We will restrict our analysis to spherical. We will not do more complicated surfaces or interfaces like parabolic or ellipsoidal. And those are all possible, very reasonably easily possible. We will restrict ourselves to spherical lenses, that's what we will call. So we are doing refraction to begin with. Ray optics. Refraction. Ray optics to begin with has this approximation that wave, if the wavelength associated with the wavelength is the periodicity in space that a wave has a property, the property of the wave involves the periodicity in space, and if that wavelength is significantly larger than the irregularities on the interface. That means if you polish a surface, and if you can decide the polishing, how good the polishing is by the small irregularities that you have, if the wavelength is larger than that, or if the smoothness of the surface is smaller than the wavelength, and typically visible light has about 400 to 700 nanometers of wavelength. That the stretch is because the red light has a longer wavelength, that's about 680 nanometers, and blue light is in the range of 400. So that's why we say it is 400 to 700. So if the polishing of your surface is the irregularities that you can develop from the polishing is smaller, that's what we say. If the polishing is smaller than the wavelength, then it is good to approximate this whole light as a single ray. So this is all you need. That's your ray, and there is no wavelength we talk about after that. It is just a direction of the line that is important. When it comes to refraction, there is another property, that is the speed of this light also comes into picture, and speed is related to the wavelength. That's also to be considered. So wavelength does come into picture when we are talking about just while it is crossing the interface, not while it is moving in a medium. When it crosses the interface, there is a change in the speed or the change in the direction. So the law of refraction states, that's it. So if you have a medium, so that's medium 1, call that medium 1 and medium 2, they're described by the speed of light in the medium. Speed of light is always slower than the speed of light in vacuum, which is approximately 3 × 10⁸ meters per second, and that's described by what is called refractive index, which is always larger than 1. C over speed of light in the medium. It is always slower, so the fraction C over V1 is always greater than 1. C is it's an integer number, that is 792,458. But for 2 or 3 significant digits, it is exactly 3.0 × 10⁸ meters per second. So as far as your experiments are within 1% accuracy, 3 × 10⁸ meters per second is good enough. And 2 is speed over V2. And we said that if you have an interface like this, light comes as a ray. If the interface, the irregularities on the interface is small enough, it is sufficient to think of it as a ray. And after it enters into the other medium, the angles change in such a way. So you have angle θ1 times the refractive index has to remain the same. So if the refractive index increases, then this has to decrease. Let's consider the scenario when N2 is greater than N1, then the angle has to decrease. So that's θ2. If by any chance N2 is less than N1, which is also possible, then the angle increases. The angle increase and decrease is governed by the equation N1 sin θ1 is equal to N2 sin θ2. And this is called the Snell. That's the primary summary of what we have done. And notice this interface is flat. We have taken it to be flat, and it can be even if it is curved. For example, if you're having a small beam of light, by beam we mean its width is small compared to the stretch, then if it is small, then even if it is curved here, it doesn't really matter. And we would like to have a scenario where these surfaces are actually curved and it is spherically curved. We'll talk about 2 types of spherical lenses this time. So we want to talk about lens now. And it is spherical lenses. This involves light going from one medium into the other. Now we want to go into the other medium and come out of the medium very quickly. So we will have situations like this. So this is a spherical surface, a part of a sphere. This is N1, that's N2, and it is N1 again. This could be air. Most of the time we are doing our experiment in air. It doesn't have to be. It could be in water, for example. This is another medium. Light comes in this medium and goes through. And there are two spherical interfaces that's involved in this picture. And one is having radius of curvature R1, and other is having radius of curvature R2. Both of them together will decide how light behaves when it goes through this what we will call lens. And for our purposes, we will just say that the focal length F. So the radius of curvature corresponds to what is called the focal length. Very similar to what we had in the case of mirrors, but that was a single radius of curvature or a single surface that was deciding that. This will be called a convex mirror or convex lens. We'll talk about how it behaves, how light goes through, and what we can talk about in a few minutes. Just to have a physical insight of what we are talking about, your eyeglasses are very good examples of convex lens or concave lens. Both lenses are used for eyeglasses. And again, I will I'll touch on that for a few minutes today. This is convex lens. There's another possibility that you could have the two surfaces in the opposite direction. So that's your radius of curvature R1, that's your radius of curvature R2, and that's the refractive index N2, N1, and again it comes back to N1. And that would be a concave lens. You might immediately ask, it is why both the surfaces should be this way. It is possible to have one of the surfaces in this form and other also in the other form. If R2 and R1 are not the same, you can have those effects. But overall, we will be interested in what is called the focal length. The radius of curvatures together lead to what is called focal length, and it is given as the inverse of the radius of curvature, and it also depends on the change in the refractive index. But here I will not talk about the focal length. So let me just stop by mentioning that it depends on N1 minus N2. In fact, if it is going into the third medium by any chance, then it is N1, N2, and N3. It depends on R1 and it depends on R2. And overall, finally, it is only the focal length that decides how, as an overall, the lens will behave. So for our purposes, we will just use the idea of focal length of the limited time that we have. Whenever you talk about the power of your eyeglasses, you're talking about the focal length, not exactly F itself, it is the 1 over the focal length we are talking about. But otherwise, it is exactly that quantity. Let's talk about how we decide on where images are formed using a lens. And for that purpose, like in mirrors, we need a sign convention. Now, the basic idea is that there is an equation for a lens and there is an equation for a mirror. And one has a choice that either you keep the equations the same and change the sign convention. That's what we will do here. Or you could have changed the equation itself and kept the sign convention the same. So here, I think different textbooks do different things. Here, I'll be keeping the equation the same and the sign convention will change. For lens, notice if compared to what you did for mirrors, there will be a slight change in the convention. It is confusing, but I will do that. And I did mention this to the other course, the tutorial course that we have I don't think the sign conventions are there in the equation sheet. But if one of you asks me to put it on the board, I will put it on the board. I will try to type it down in the equation sheet itself. I'll try to update that. But if I do not do that, you don't see it. Just one of you, if you remind me, then I'll put it on the blackboard for all of you to have that. And hopefully I don't make an error on that blackboard when I'm writing. So that's for your information. So let's say sign convention. Let's begin with that. For lenses, we have the direction of light. Light moves in a certain direction. That's called the optical axis. And somewhere in between, you keep a lens. This time you have two possibilities. You either keep a concave lens or a convex lens. So this line represents a lens. Two possibilities: either it is this or it is this. That's a convex lens versus a concave lens. Whether it is a concave or convex, the primary difference is the focal length, the sign of the focal length. It is a positive focal length. That means it is to the right side when I'm facing the blackboard, and that's a convex lens. This is also called a converging lens. If it is negative, it is a concave lens, and it is also called a diverging. Diverging in the sense that light tends to come out of a certain point instead of going towards a certain point. This is different from what we had for mirrors, so make sure you have the nomenclature and the sign conventions right. Object is usually kept on the left side when you're looking towards the blackboard, so usually you will put that. So that's your real image, and you would say that's positive. So this will be a, sorry, I said image, I think real object. And that will be the 0, that's or the O, the object distance. And this is a virtual object. We will not have the opportunity to talk about or discuss virtual objects here too much, or especially the examples. But it is possible to have virtual objects, especially if you compound your system. If the image of the first configuration, either a mirror or a lens, serves as an object for the second lens or a mirror, then it is possible to have virtual objects. And where do you have these compound situations? The simple, most popular devices or instruments would be a microscope or a telescope. Both of them have at least 2 lenses or mirrors in them. Image distance is where the image is formed. We would like the image, typically the image is formed using a lens on the right side. So you give that positive sign. So that's your positive sign. So that's a real image. And if that's the situation, if an image is formed on the right, then light converges to that, and you will feel a warmth wherever the image is formed, if you keep your hand. This is negative, and that's called a virtual. There are often concept questions that is asked out of this table. For example, what is a virtual image, or what is a virtual object, or why is a concave mirror a diverging lens? Those kind of simple questions, which is used for in the analysis of an actual homework problem. This is all left and right, which is useful for ray diagram. There is also up and down. You say this is an upright image or an object, and this will be an inverted image or an object. Most of the time when we talk about an object, it is you begin by an upright object, and you get the image could be either upright or inverted. The size of the object, also magnification is positive if it is larger and upright. It could be negative if it is small, it could be whatever the size is, and if it is inverted, then the magnification will be negative. So that's the parameters or the conventions that come in, and let's do examples now. And what are the typical examples, specific examples that you use both your eyeglasses serve as both concave and convex lens. So that's the best example. Sometimes it is a power when you are correcting yourself for long range, long distance vision or short distance vision, whichever one you use, that's the opposite of each other. Which one exactly it is, I don't remember now, but when we are talking at the end, I will describe how a lens is used for correcting your eyesight. At that time, I'll specifically point out which one is which. Let's begin with an example of a convex mirror, convex lens. The moment I say it's a convex lens, the focal length is positive, and let's say it's plus 10 centimeters. I decide on the optical axis, keep your lens somewhere here, and that's your lens. I clarify that I'm not drawing the lens itself down here, because then it leads to the confusion as to where does the ray reflect from. So it is good, this is only a scaled model, so it is good to use the line as your for the purpose of drawing. Use this line as a reference point, and this gives you the idea that we are talking about a convex lens. The moment it is plus 10 centimeters, that means there is a number here, that's your focal point. Right, it is plus 10. Notice the sign convention says plus means to the right. That's your plus. When you're drawing your ray diagram, you don't want this to be exactly plus 10 centimeter. We have already learned that you use a chart, right? This could be 1 centimeter is equivalent to 10 centimeters, and everything on the x-axis or horizontal line will be in repetitions of 10 centimeters. It doesn't have to be the same scale in the vertical direction also. You can use a different scale. You should use a different scale, because this one will be 10 centimeters and the object might be 1 centimeter high. So you want to use for height also, you want to use 1 centimeter on the paper and 1 centimeter representing 10 centimeters for the horizontal line. So make sure you do those things. That's where the practice comes. Make sure you you learn to draw some ray diagrams on your own with the scales involved. Remember, I give some significantly good points for the ray diagrams to be correct. So I highly recommend that you practice ray diagrams for these problems. That's the focal length, one focal length towards the right. So that's 2, and that will be 3. That's minus focal point, minus 10 centimeters. That's minus 20, and that's minus 30. So that gives you a distance of scale if you want. Let's say the object distance, object is placed, one can place anywhere down here. Let me place it 20 centimeters to the left, so that means object distance is plus 20 centimeters. Notice I have given it to you as an equation. Most often in your problem, you'll have to translate that. The problem might say that you have a converging length of 10 centimeter focal length. So you have to read out that this is what is length, and if it is kept 20 centimeter in front of the lens, then you have to gather that it is the object distance that is being talked about, and it is 20 centimeter. I try not to be tricking on those things. I try to make it plain and simple. So if you think that's what is being talked about, most probably that is what it is. So object distance is the distance from the lens. So we have an object that is placed here, and that's also put the idea that the height of the object is plus 1 centimeter. That means it's an upright object placed it is 1 centimeter high. Notice this is 1 centimeter, and for all you know, you might have used 10 centimeter to represent 1 centimeter. You can also use 2 centimeter to represent that. So the actual distances are different from the scale that you're using. So that's your object. That's the length, and you would like to find where the image is found. Remember, to find where the image is found, we usually want at least 2 rays of light, at least the rules for that, and we would like to know where the image is formed based on that. Exactly right, exactly like in the case of mirrors, you start the first ray going parallel to the optical axis. Remember, even in the mirrors, you started by going parallel to the optical axis, and after it reaches the mirror or the lens, you go to the focal point. Same thing in the mirror also. You go parallel to the optical axis, and after you reach the mirror, if it was a mirror, then you reflect, and the focal point will be here or there, and it goes through the focal point. Here, the focal point, positive focal point is to the right, so you go through. So this is your convex lens. So that's the ray 1. So that's ray 1. Go parallel to the optical axis, and after you meet the lens, you go through the focal point. That's your first ray. The second ray in mirrors, you again went through the radius of curvature, which was 2 times the focal length, and that ray goes undeviated. In this case, there is no radius of curvature. Instead, you have the center of the lens. A ray that goes through the center of the lens, that goes undeviated. So you start from the head, go through the center of the lens, and it goes undeviated. That's your ray 2. That's ray 2. So again, the first ray go parallel to the optical axis. After it meets the lens, go through the focal point, and the second ray goes through the center of the lens. When you go through that, it goes undeviated. Either it can come back or go through it. So it doesn't change any direction at all. And where would it be? That's where the image is formed, the image of the head of the object. So you draw a line either inverted or upright with respect to the optical axis, and that's your image. And it seems like when you look at the diagram, if I did it all accurately, then it seems like it is an inverted image, and it is also magnified. It looks bigger. Is it a virtual or a real image? Look into the chart. The virtual image is when it is on the left, so on the right it is positive. So this will be a real image. So the image is real, it is inverted, and it is magnified. So it is real image. It is an inverted image, and it is magnified. And that's the 3 properties you can conclude immediately. Let's try to see this analytically. We have equations for this. We have the equation remains the same as I mentioned earlier. The 1 over the object distance plus the 1 over image distance is equal to 1 over focal length, exactly the same formula as we use for mirrors. It's the same for lens and mirrors. So it is 1 over object distance is plus 20. Image distance is what we are finding typically, and the focal length is plus 10 centimeters. 1 over 10 minus 1 over 20. So that's 1 over 20. And seems like image distance is 20 centimeters. It is positive. Positive means it is real. Tells us that it is real, and it did come out real. It came out on the right side. Notice it should have been 20 centimeters. So if I had drawn this accurately, this image should have come out here. So this should have intersected down there. And that's because I have not been accurate enough to draw perfectly straight lines. So this should have intersected here, and the image should have been formed there. What about the magnification? And this will lead to an error here, and that's a good description of how errors come in the ray diagram. So the magnification is minus of the image distance over the object distance. That's minus of 20 centimeters. And the object distance is also 20 centimeters. So that's minus 1. The minus tells you that it is inverted. And 1 tells you that it should be the same size. So we did get the inverted correct. And the real part correct, but it should not have been magnified. That's because I was not accurate enough in drawing the straight line. So this is wrong. It should have been the same situation.
So in the second part, we're supposed to pass to the radius curvature.
No, there is no radius of curvature for a lens. There's a center of lens. So the wherever the optical axis and the line representing the lens cross or lens cross, that's the center of lens. So let me write that out. This is center of lens. So a line starting from the head of the object and going through the center of the line goes undeviated. There is no bending of the ray. Yes, sir.
What does magnification have to be for it to like get bigger or like get smaller? Is it like bigger?
If it is greater than 1, let's say it was 1.2, then it is magnified, that is larger. If it was 0.8, then it is smaller. Anything greater than 1 is bigger, anything smaller than 1 is smaller than the actual image. That's a plus and minus 1. Minus 1 means it is inverted, plus 1 means it is upright. The minus side told us that it is inverted, but my diagram was not good enough for me to be able to capture the fact that this should have been magnified. This remains the same. So this is wrong calculation here. It remains the same, and that's why the actual calculation out remains the same. So always the ray diagram and your calculation should be consistent, and you want to check one with respect to the other. Any questions on this? We can also get the actual size of the object. In this case, it will be the same because it is not changing the size. There are 2 ways of doing that. One is we use the magnification formula, which is height of the image over height of the object. Or you can set height of the image equal to height of the object exactly equal to that. Either way. So magnification was -1. height of the image over height of the object we said was +1. So this implies that height of the image is equal to minus 1.0 centimeters. Any questions or queries, comments? Let's do an example on concave lens. I should also point out how things can change. Notice that when I move my object between this point, second point, and third point, whatever I do, the ray 1 still keeps going parallel and it will still keep going to the focal point. So ray 1 practically remains the same wherever you keep your object. That's not what decides where the image is formed. It is the second ray that decides where the image is formed. For example, if I move my object farther, I'll try to put this on the same diagram. If I'm going to put my object a little farther, so I'm moving this away, and we want to ask what happens to the image, where will the image move? Now draw the new rays. So again, this will go like this, and it goes through the same ray 1 is repeated. But the second ray now, is try using the dotted lines, has to go through the center of the lens and keep going. And it is down here. That's your image. Earlier the image was formed here and or inverted, so it was down here, and now it has become smaller. Like you can make judgments just by drawing the or moving the rays in your head that it is getting smaller and smaller. As you move this farther and farther, this line will bend, the dotted line will bend, and this will get smaller and smaller. So those judgments you can make, and that's how the problems will change. This will not be 20 centimeters, this could be 30 centimeters, it could be 10 centimeters, and the properties of the image can change significantly. Let me stress that a little more. If I were to do the opposite, instead of going away, if I were to move to the right, so this dotted line, this time I'm moving to the right, you will notice that this is not moving this way, that is moving farther and farther. And once you reach the first point, that is the negative of the focal length, this ray, the ray 2, will become parallel to ray 1. Ray 1 and ray 2 will become parallel. That means that this intersection of these two rays will happen at infinity. So the image will get really huge. They get larger and larger, and at some point it becomes infinity. But you have only been here. The object is at this point. You can actually move further into it, closer to the lens, and then you might wonder what happens to the image. So the image is already at infinity. There is no more distance for it to go. Where does the image go? It changes its properties altogether. It is no more inverted, it is no more real, it becomes virtual. All the way from infinity, it jumps to the left side and it becomes negative infinity. So let me try to draw that for you here. So that's another color. No. Oh, I'm excited. But that's almost white. It's the same idea. Is this white? Better, maybe. So you make this object go closer and closer, and we're talking about what happens right at this point when it crosses this line. The image takes a sharp turn. Ray 1 remains the same. Ray 2 now has to go through the center of the image, and you see that these two are making a cone not this way on that side, so that is not going to intersect. Right, this is the cone is increasing in size. It doesn't intersect on the right side. Instead, it intersects on the left side. Light is not expected to reflect when you're talking about a lens, so that's a virtual image. There was a real image, and you move closer and closer, this becomes larger and larger, and at some point it will jump from positive infinity to negative infinity, and then it gets closer and closer on this side. So that can be seen. You can actually move the lens in front of you, and if you think of what is happening to the image, you can see this or imagine this to be happening inside that mirror, and this will be your image. Not that this need not be accurate enough, it could be on this side or that side. That's for convex lenses. Let's do the same for concave lens. Concave lens, let's say the focal length is again plus 10, no, minus 10. Concave by definition is minus 10 centimeters. Let's say the object distance is plus 20 again. And let's say the height of the object is plus 1. Real object, the negative sign means it's a concave lens. Plus 1 means that it's an upright object. Have the optical axis. That's your position of the lens. That's a concave lens. The diagram there tells you that that's a concave lens. It's minus 10 focal length, so the focal length this time is on the left side. That's minus 20, that's minus 30, that's 10, 20, 30. So if all the distances are accurate enough. I said that it is placed, the object is placed 20 centimeters, so this was minus 10 as far as focal length goes. But when I'm talking about object distances, this is plus 10, so that's plus 20, and that's where the object is. Like, remember, object distance is positive to the left when you're looking on to the board, and focal length is negative to the left. The rules remain the same. You go parallel to the optical axis, and you go through the focal point, but this time the focal point is onto the left, and light is not expected to reflect off a lens. It is supposed to keep going, so light will keep going, but it will pretend as if it is coming out of the focal. So light is going that way, but it is pretending as if it is coming out of the focal point. So it does go through the focal point, but in a virtual sense. Or this is what is called a diverging lens, right? The convex lens, after it reached the lens, it converged towards the optical axis. Here it is diverging away from the optical axis, and that's why it's called a diverging lens also, as far as convex or concave lens goes. So that's your first ray. The second ray goes through the center of the lens. Remember, the center of the lens is the intersection of the optical axis and the line representing the lens. So start from the head of the object and go through that, and that the ray goes undeviated. Start from the head, go through the center, and that goes undeviated. So that's ray 2. And that's ray 1. And wherever the intersection happens, that's your image. That's the image. And we can say it is virtual because it's on the left. So the virtual image, it's an upright image, and it is smaller, or it's diminished. Let me say, right? That's the three properties you can think of, and you immediately can verify this. 1 over object distance plus 1 over image distance is equal to 1 over focal length. 1 over object distance is 20 plus 20 plus 1 over image distance is equal to 1 over minus 10. So our image distance is minus 1 over 10. That's 1 over 20. So that's minus 2 and minus 3, right? So it's minus 3 over 20. So image distance is minus of 20 over 3. That's minus 6.7 centimeters. Okay, and that's supposed to be 10 centimeters. It seems like we got that distance 7 centimeters approximately. Correct. Now coming to the height, the magnification is minus of image distance over object distance. That's minus of image distance is, let me write it as minus 20 over 3. 0.7, that's good enough, but and the object distance is 20. So that's 1 over 3. And that's plus 0.33. Like there is no units for magnification. The plus tells you that it is upright. And here also I should say the minus tells you it's virtual. 6.7 tells you how far it is from the lens. Negative tells you it's virtual. Plus tells you it's upright. This being less than 1 tells you it is small or diminished. You can also get the height of the object, the height of the image over height of the object. Notice there is no sign there, plus or minus. So it's let's say 1 over 3 is equal to height of the image over height of the object is 1 centimeters. So that implies that height of the image would be plus 0.33 centimeters. You can do the same analysis that we did for convex lens for this. What will happen if you were to move this mirror away or closer to the lens? And you will notice that, or you should ask yourself, where should I place the object so that the image becomes real? And you will notice that as I get closer and closer, I will always have room for a ray to go through this and it will intersect this line. If I go farther, this gets smaller and smaller and it will almost reach the focal length. And as I get closer and closer to the lens, this gets bigger and bigger, but all through it stays in here. So using a concave lens, the statement is you can never have a real image. A concave lens cannot give you a real image. The image is always virtual. So that's a conclusion you can make using the simple ray diagram. Let me say in very few minutes how correction glasses works. Very qualitatively. Eyeglasses. Eyeglasses for correcting your sight. This is going to be very simplistic, extremely simplistic, so don't be too critical about it. A simple eye is having a natural lens. It is typically convex in shape, and the nice feature about this lens is that it has an adjustable focal length. Our lens that we have, that we are born with, our eye lens is flexible in the sense this is a tissue, and you can pull this. The muscles here connected, so these are muscles. So when we pull on that, it changes the spherical curvature of this lenses, and you can increase or decrease. That's why when you squint, that you're trying to see farther or closer, you're actually using your muscles to change the radius of the wafer. Again, simple thing, but broadly, that's what is happening. So muscle control F. So in that sense, very different from a microscope. If you're looking, if you have seen through a microscope or a telescope, you have to tune it. So you have to change the distances. That is the only parameter you can have. Here you can change the distances and the focal length. The lens sits in front of a fluid. That's a eyeball, if you want, and at the back side of the ball, there is a thin, what do you call that? It's a retina. That's what. But for simplicity, we say there are sensors here that can sense red light, green light, and blue light. 3 colors it can sense. Right? And all those sensors come together and go to the brain. That's the brain. Where the analysis is done. So there are some sensors, red, blue, and green at each point where it is formed. And this retina is basically what acts like a screen for us. Like if you were doing an optical experiment and you keep a screen to see your image, that's what your retina is. Sometimes if you get an injury or something, this can get dislodged. There are 2 injuries that can happen in an eye. Sometimes it is a lens that get affected. It's very easy to change the lens. It's almost an outpatient department. You don't even have to get admitted. You go in the morning, within an hour, they will fix your lens. They will basically take this lens out, put this lens, replace that lens, and then you can leave within an hour or so. It's a very easy surgery they perform. But anything happens to the retina cannot be fixed. As of now, there are very limited developments made so that you can deal with this. I have my retina spoiled. That was an injury. If you're noticed, I have my eyes look different. So my retina is completely destroyed. It happened very long, but that's not important for the course. So that's your lens. And now let's say that as you get older, or for various reasons, your muscles might get weaker, and you may not have sufficient power to control that that lens. Let's say, see, there is an object here, and I'll have, instead of having an arrow, let's just represent it by a single line, and that's your optical axis. And broadly, what is happening is that light goes in here. Basically, this lens converges. This is the convex lens I have shown. It is supposed to converge this light, and it is supposed to reach exactly this point. If it is a sharp point that is formed, the image is exactly formed there, then we see the object as a sharp point. If by any chance, if we are not able to control this focal length sufficiently, what would happen is, so now we are weaker, we are not able to pull this sufficiently, so we are not able to make it converge there. So it doesn't stretch in here, instead the image is formed somewhere there. And you will see instead of a point pattern, this becomes fuzzy, right? The object has stretched instead of a point, it is fuzzy, and that's all. If you remove your glasses, things look fuzzy, right? That's your point becoming fuzzy. Yeah, that's the word. Yes. Now you want to correct this. A very simple correction, pretty nice, clever way is that within the natural eye lens, you put in another lens in front. You want to bring in, you want to make this converge, right? You want to converge more. So you would put in another convex lens this time. And this right here bends a little, a little. That's what you check with how much you want to correct. That's what your doctor decides. And this will make sure that your head, now your muscles don't have to do this much of a job. You have provided your head, your muscles, and now it is possible for the muscles to do the rest of the job, and you make it a sharp image. And that's a corrective lens that does one of the job, either long distance or short distance. Let me not. Yeah, that's, I'll leave it up to you guys. Convex corrects it for long distance or short distance. I'll have to think about it here at this point. Sometimes it is the opposite. It is not the, it's your muscles are not doing the opposite job where it comes in here. So that happens when you get older. So again, let me draw this lens here. So that's your natural eye lens, and this time that's your image. This time it is image is being formed closer. So again, it is fuzzy, right? By the time it reaches the brain or the retina, it is fuzzy. This is your actual. This is where the intersection is happening, but you want this intersection to happen on the retina. So you want to help your eye. So this time you will place a convex. Did I say concave lens? This time you say concave lens. Help it a little. It goes farther, and in such a way that now, if it is going farther, it will go in here. That's a very qualitative way of describing what is, but pretty much mostly that is exactly what is done. As far as inside part of the eye, that is complicated. I have made significant simplification here, but this part is pretty much accurate enough, and that's exactly what is done. Some of the challenges in this is that how much you want to correct is pretty much based on your response. You stand there in front of the doctor, and they ask you to read a line, and whether you can read that or not is what tells you whether this has done a good job or not. And one of the challenges, if you are a kid, especially a toddler, then how do you get this feedback from them? So if you can make a sensor that you can look at and get some spherical curvature out of that, those are the challenges that comes in. As far as the outside part goes, inside there are significant enough challenges. You should be able to talk to someone at a doctor for that. I'll stop the course here. This is the last day. I don't mind stopping it a little early. Thank you for listening.
Thank you.
Thank you.